Hello, good afternoon, everybody. Welcome to this afternoon's oral session. We are on T4.4 in case you'd like to know which session we're on. And that session is Network Sustainability and Systems Engineering for the CTBTO verification technologies. So without much ado, let me very briefly introduce, we're going to have three presentations today. The third presentation officially of the program has been withdrawn. So instead of having a gap, we'll move directly from the first to the second, and then without a gap, we'll move to the fourth one immediately after the second one. So the first presenter today will be myself, Nick Mascarenhas. I'm the head of the maintenance unit at the CTBTO in the IMS division in the monitoring facilities support section. And my talk today will be activities to improve data availability by the IMS maintenance unit. So without much ado, I'm Nick Mascarenhas, again, head of the maintenance unit. And my talk is about all the work that we've done specifically to improve data availability. Next slide, please. So a brief outline of the presentation today. There are some key methods that have been put in place by our unit that have led to improved data availability. And I'll go over and show you some examples on each one of these key measures. Very briefly, the first one is equipment standardization. I'll be talking about infrastructure improvements, power grounding, lighting, air conditioning, humidity, improved spares, improved technical training and documentation, and a little bit about some proactive work we did on gamma detector vacuum restoration, monitoring for failures before they occur, and also some measures to improve the handling of detectors to enable them to last longer in the field. Next slide, please. So the first one, as you know, our stations are in very difficult and remote locations, and most of them have significant equipment, very specialized technical equipment, be it radionuclide, noble gas, particulate, digitizers, detector systems, seismic sensors, infrasound sensors, hydroacoustic sensors. All of this has to operate on harsh environmental conditions. Were there not particular systems put in place to keep the environment clean and particularly not hostile to the equipment? So we have climate control. And in order for it to work well, we really need to make sure the climate control equipment is properly working, adequately serviced, and then replaced at the appropriate time. Also, power and grounding is really important. So we need to make sure that the grounds, when they are in place, are serviced regularly, are tested. There's the middle picture you can see of a test being done to measure the grounding. When it's out of spec, then of course we will take measures to improve it, to bring it back into spec or replace it if it needs to be replaced. On the left, on the bottom left, you see a guy installing a power conditioner. That's one of the things we found was very useful. In addition to the power that we secure from our local sources, we sometimes found it's necessary to improve the UPS that's installed in many of our stations, a power conditioner, which then improves the quality of the power further and protects against spikes and other damaging things that can come down the line. And last but not the least, on the rightmost corner, there's a picture of a backup generator. Many of our radionuclide stations, it's mandatory to have a backup generator in case the power fails. And you really have to make sure that they're tested, that they're in good service condition. And the picture on the right is for Kiribati, where we exclusively run a generator. And in that case, we actually had to replace the failing generators by air-cooled gensets after it was found in the marine environment that they couldn't last very long and led to serious problems at the station. Next slide. So sparing, as you can imagine, data availability requirements mandated are quite strict, especially in the radionuclide. We only allowed 7 days consecutive in a year to be down. And in order to do so, if a part is required to be a spare or replaced, it's very difficult to ship it to outside of the world from either depot or headquarters. So we invested in the policy where certain critical equipment, we have it spare at the station. For example, digitizer, or a computer for the station, or high voltage power supply, and so on and so forth. By keeping these spared right at the station, we were able to improve data availability. And the pictures there show you some of the systems that we put in place, just examples of 2 digitizers on the left-hand corner. Similarly, for the case of the other technologies, seismic and hydroacoustic and infrasound, we actually spare equipment at the station when there are multiple sensors or multiple digitizers at several sites. Then, a sparing analysis is done, and we make sure we have enough on site in case something's needed to be replenished right away. Next. Training. In order to do the right job, the station operators need to know how to do the job correctly. So training is a critical part of the work that we do. And you can see pictures there of our staff training the station operators on site. Hands-on training is really important, as well as we have training conducted here in Vienna or conducted by some of our contractors, experts in the field, who then take them to their facility and train the operators on what to do. To complement the training, we also have specific procedures written, and those procedures have to be clear, detailed, and complete and tested. And these are called the SOP, Station Operation Procedures. So a lot of work in both the training and operating procedures goes into keeping the systems running and allowing maintenance to be done correctly. Next. So here's another thing that we found for radionuclide detectors. The critical part is in a germanium detector is the vacuum. And we found that by monitoring the detector temperature or the cooling power, depending on the vendor for the detector, it was possible to actually detect a failure or impending failure or deterioration of performance well before the actual part failed. And if so, then we can intervene. A picture shows you the equipment that we use to go on site or bring the equipment back when we intervene and then restore the vacuum and then quickly bring the system back into operation. So this has been successfully done, reducing our turnaround in many of the stations, for example, Fiji, Iceland, Chile, Portugal, Germany, Cameroon, and many, many other stations. It's now very often used vacuum restoration to fix detectors, and all our staff and maintenance are trained on it and can quickly do this. Next slide. So here's something that we implemented. Our detectors are shipped to very remote sites, and the course of shipment, the normal boxes that are used by vendors for shipment don't provide adequate protection for the equipment so that it sustains the damage that can occur if it's dropped or mishandled during shipment. So we developed specific belly cases with foam inserts, worked with the manufacturers, and after implementing this, we significantly ruggedized the cases and handling and reduced the detector failures. Next. Here's another important thing. The network is about 20, 25 years old now. Many of our stations, in the due course of time, the equipment becomes very varied, some of it obsolete. And one of the key measures things that we've been doing right now is standardizing, especially the RN stations, all the stations. The RN particulate stations, all of them look the same, okay? They have the same weather station, the same model computer, the same type of digitizer. There's one of 2 types of detectors used, and so on and so forth, yeah? But by standardizing equipment, we can provide a much better level of service, and we understand the behavior of the equipment a lot better. It's very hard for a system with hundreds of stations to sustain it, if each one has a different identity. So standardization is a big thing. Next slide. So here you can see a typical radionuclide particulate station and the key systems in it, the computer, for example, or the blower, Snow White, or the Ethernet switch box, or the DAS for measuring all the I/O, temperature, humidity, the digitizer, all of these, the barcode readers, all standardized. And in doing so, we have significantly reduced our problems and also increased our ability to provide the maintenance that's needed and service that needed when it is needed. Next. So data availability, what's the effect? Improvement. Here's the last few years shown in this slide. And you can see we're reaching very high levels already, well above 90%. In the case of radionuclide, almost reaching, in 2020 and 2019, almost reaching 94%. In 2020, that was COVID, and especially the noble gas technologies are highly dependent on the service vendors visiting the stations, and visits were not possible under COVID, so you see a little bit reduction. But generally, a huge uptrend in data availability, which is a key performance indicator, after putting all these measures in place. Next one. So I told you the data availability when we started all of these activities was about 84%. Now it's reached about 94% after the measures were put in place. Some of the challenges, the network is getting old, so we have to deal with a limited budget on sustaining an aging network, which means sometimes replenishing parts or recapping a complete station. We're still building a few stations and completing the network, so there's a lot of work that we're doing while we're sustaining the rest. We have a fixed number of staff, a fixed number of funding. So the future actually exists, and the promising things are things like predictive maintenance. The next talk will be about such measures, and we hope to then you'll hear about that. So after this, I'll be happy to hear from you guys on if you'll have any questions. But just the last thing I'd like to say before I end, the measures that we put in place were measures that's going on for the last 6 or 7 years. But under COVID, which is the last 1 year, one of the key things that we've been doing in terms of special measures is taking extraordinary measures to improve data availability. For example, increasing spares over and above the spares that are needed, or finding local sources of supply, or providing remote technical assistance when experts can't go. Some of our successes are, I'll just mention, in the case of Mexico, we had a noble gas sauna system, which was down for an extended period of time. The gas chromatographic unit was broken. Vendor couldn't go there, but we sent the gas chromatograph, and then our maintenance officer, with the help of the vendor, remotely had the station operator install it and successfully restored the station. So with that, I'll end my talk, and I hope that y'all have some questions for me. I'll be available to answer. Thank you. Okay, so I think we don't see anything coming on the Q&A right now. So without much ado, I would like to ask Ray Suarez. Our next speaker will be Ray Suarez from PNNL Labs. And Ray will be talking to us about advanced algorithms and prognostics for monitoring the Radionuclide Aerosol Sampler, the RASA. Ray, we'll play your presentation.
Hi, my name is Ray Flores, and I'm from Pacific Northwest National Laboratory. Today, I'm going to present on some work that we've done for monitoring the Radionuclide Aerosol Sampler and Analyzer that's in the IMS. So in July or August of 2019, the sauna at IMS Station RN77 had a sampling pump failure. Our current diagnostic techniques and monitoring techniques caught the failure somewhere around the 11th of July. We've been analyzing this data really closely with some AIML techniques, and it looks like we may have started to see features 2 weeks earlier. That's some ongoing research. What if I told you we could have detected this failure 3 months earlier, or even 6 months earlier? And furthermore, what if I could have told you not only when this was going to fail, but how it was going to fail? And that's really the goal of this work, is to detect failures early and detect how the systems are going to fail. So how do we do that? How do we get there? So it's really important early on to engage operators and experts. You need feedback from them, the ones that are out there and have lots of experience. We need to make sure you're engaging them. We need to have tools, state health monitoring tools that are very scalable and system agnostic, with the ability to read in different types of data and sample at different rates and use different algorithms. Tools need to be capable of using some basic diagnostic algorithms and some more advanced diagnostic and prognostic algorithms. So we have to be able to use different types of algorithms with that same tool. We then have to start looking at the latest advancements in data science and start to look at data-driven and physics-based models and help us identify those failures early using the current IMS state of health data. We need to be able to identify where there's gaps in data. What other data do we need that's going to help inform our predictive analytic techniques? And when we find those gaps, we need to strategically look at sensors that are going to help us provide that information that we need. And lastly, we need to continue to use the data science algorithms to incorporate the new sensors that we've identified. So when we talk about state health monitoring, as many people know, radionuclide systems have hundreds of sensors associated with them. Those sensors are typically sampled on some given interval. In the IMS, those are sampled in 10-minute averages, and they're sent out in 2-hour files to a data center. And these sensors are things like pressure, temperature, flow rates, voltages and currents and this type of information that are typically used for diagnostics and detecting failures at a station. So the state health monitoring that P&L's been doing, we've been working on this for many years. And what we did is we've been working really closely with the US IMS operator, General Dynamics, and we communicate with them quite often, and we've gathered requirements. The other thing that we've done also in the past is we've engaged the PTS on feedback. So we use that information and we developed a suite of tools in an architecture for state health architecture. And that architecture is capable of ingesting data. It's capable of providing both automated and manual analysis, running different algorithms, and provides a user interface with some dashboards. And then our initial concept was to start with some simple models and then move over to some advanced models. So we started with Asana and developed this architecture with Asana, and then we've extended it now to RASA, which is what we are discussing here today. So the architecture, like I said, it's very scalable. We can run algorithms in parallel. Our sensor lists are dynamically built. We use a database to house all of the data. We have a standard interface to the analysis algorithms. Right now, what we're doing is using IMS 2.0 as our format, and it also provides a web-based graphical user interface that I will show here in just a second. So the unit provides some dashboards, and this is where operators can look at a station and understand what's going on. On the left, what you see here is a map, and I've highlighted an icon. And what's interesting about this is this happens to be for a noble gas system, and what you see in green is an indicator that the xenon volume, which is one metric that's typically used, is green, meaning I'm meeting the amount of xenon I need to collect in terms of how many cubic centimeters I'm collecting. But the station itself is red, so that means that while I am collecting the amount of xenon I'm expected to collect, there is an issue at that station. So you'd want to click that and get more information. And on the right, it's just similar information, but it's in a ticket format. Once I click a station, I get a pop-up window. In this case, I'm looking at a RASA at USP 71, and it will highlight the sensors that are causing the alert. And if I want to dig further into that, I can click the graph button to dig down into that sensor. And what you'll see is there's a State of Health Explorer window. And when you look at that window, what you'll see is that sensor plotted for the previous 2 weeks, and you can see when in time that failure was generated. And at that point, you can actually plot other sensors to see if they're also failing and do more diagnostics in that way. If you want to do some manual analysis, you can also go to a different tab. You can select your station, your sensors, and you can click and run some algorithms that are already in the tool. So we also provide a State of Health Model Manager, which is a way that we were able to build models. And the neat thing about this is it's scalable. So I can build a series of State of Health models that consists of one or more sensor models. And you can build up different libraries in that way, depending on how and what you want to monitor. This is all web-based, and so if you're interested in, for instance, doing a query from the URL, you can do that. You can share a URL with your coworker or colleague, and they can get the exact same view that you have, and all the data can be exported to various different formats. One other additional nice feature is that you can plot different system types on a single graph. And so, for instance, this is at RN75, I'm looking at a SANA, a RASA, and a Xenon International that was there during some testing. And you can start to look for correlations in the data between the different systems at that station. So in terms of the algorithms that we implemented, what we started with was some simple limits. So if you want to build a model around a sensor, you can put bounds around it. That's one way you can do it. And another thing that we've implemented is a standard deviation method, which is very similar to what you might have seen in control chart theory. Another algorithm that we have in the tools is an exponential weighted moving average. And this is important because what we found is when we started doing some analysis on some of the sensors over extended periods of time, you'll see seasonal effects. And to try to mitigate some of the seasonal effects, this exponential weighted moving average, the model will dynamically change based on what you set for your alpha or weighting factor. And so this is essentially similar to what you might see as a weighted moving average, but the weights are distributed exponentially. And so, so this technique works well for some of the data. And we have implemented some other models like a linear regression, and adaptive triggering is something that we've implemented to help against false positives. And what that does is means that I have to see so many alerts within a window, and it's user settable before I actually raise a trigger. In terms of how we do our predictive analysis workflow is we access and we explore the data, we're doing some pre-processing, then we develop those predictive models, and the idea is that once we develop those and test them, that we can then integrate them into our current system, and Envision is what we call our State of Health tool. We did some work using some data science techniques for SANA, and what we did was we took one of those techniques known as a long short-term memory technique, and we moved that over to RASA data and did some testing. And what we found was by just using a limited training set, we were able to easily move that model over, and it quickly detected a failure. In this case, this was a ripped filter on a RASA. And so it was kind of nice to see that worked well. And then, and right now we're investigating, classification technique. But the nice thing is this was a model that was generated on the SANA with the tool we were testing, and right now we're looking at this same technique for the RASA. So, I talked about predictive maintenance and how do we get there. So right now, we've developed a framework that can ingest data and analyze State of Health data. We've leveraged feedback from operators and experts in the field. We've developed some algorithms, mostly on the diagnostic side, and we're slowly moving over to prognostics. We added RASA to the architecture, which was really important. So we now have SANA and RASA. And we're currently looking at some data science techniques to analyze the state of health data that's available. So moving forward, what we want to do to help us get to predictive maintenance is, number one, identify sensor groups that not only provide us the alerts, but maybe classify the failure, tell us more about what the failure is. We want to also identify gaps in data, number two, and then we want to figure out what sensors we might add and put in place to help mitigate those gaps and fill those gaps. And then we want to look at correlate failures to help with those predictions as well. Basically, look at the entire feature space. And so by doing those, we're trying to push into the prognostics area with these radionuclide systems, and this work continues to move forward with this tool. Thank you for your time, and if you have any further questions, please feel free to reach out to me.
Okay, thank you very much, Ray. Very interesting presentation. We have some time now for people. Just remind you that feel free to post your questions on the Q&A site on the online forum and address it to Ray and then the topic and talk, and then ask your question. And then we will actually pose it to Ray, and then he will be able to answer you. So we welcome any questions. At this point, there aren't any questions that have popped up. So I'll take the opportunity to ask Ray, in terms of, Ray, how do you see, we saw a lot of development work. We saw some early kind of prototypes, and what's your idea as a developer when you'd like, and what's your time chart, your progression chart, when you'd like to go from building something that's being just tested out by experts to something where you'd want to work with a vendor or actually the PTS to incorporate maybe in the IDC or the vendor system when it goes out in the field? And what's your time scale with the current systems we have? How long will it take to get from where we are to where you think things like these will begin to become, used not routinely, but more and more?
Thanks, Nicholas. Can you hear me?
Yeah.
Okay, so that's actually a really good question, and something that we're actually moving to. So we have a data science team that's been trying to tackle this problem, and what we have done is right now we're taking some algorithms and actually trying to get them fully implemented into the software that we have, and test them to ensure that they do better than the current conventional statistical algorithms that we have in place. So when I talk about wanting to run algorithms in parallel, one of the main reasons is if I can solve something with a simple equation versus using some artificial intelligence technique, then we'll go that route. So what we're doing right now is taking some of those techniques, we're actually implementing them into the software program, and we're testing them to ensure that they provide the information that we need, whether that's a prediction of a failure early. And then number two is once we do that, we'll be doing, continue to do a little bit of testing, and then see if they work and they're able to give us that information early. That's something that we're actually doing, that we have ongoing right now, that we are doing for our sponsor. And but one of the things I did want to mention that's I think a really big key to this is I believe that we will do the best we can do with the data that's available. I think but I still believe that there's small gaps, and you had a really good example of a failure of a turbo pump, for instance. And I think if we are strategic about identifying small sensors that are maybe passive that don't necessarily take a lot of effort to get into a system. That might even help us move this further. You know, I believe we'll get better, but I think there's tons of room for improvement in that area. So, but anyways, to get essentially to your question, yes, we're moving on that, and I'm hoping this fiscal year we'll at least have some algorithms implemented that we can actually test against and continue to push that forward.
Okay, thanks. Any questions? Okay, so there are no further questions here, but I encourage the audience. This is international scientific symposium and conference, and the very nature of such type of events is for people, the participants and the speakers and the community to engage with each other, to get to know the work of the other people, to begin a conversation. And presentation is one part of the conversation. The second part is for the users or the interested parties to contact and communicate with either Ray or myself or the other speakers. We encourage you, not necessarily if you don't have it ready here, but you have the email of the participant in the program, you can contact them or continue to send questions in the Q&A here, and we'll forward them to people. We just got one question for you, and the question is, when predicting high purity germanium failures, have you reached out to see what experience they have and what parameters are important for detector failure? Was that related to me or to Ray? To Ray, yeah. Ray.
So
the question is, when predicting high purity germanium detector failures, have you reached out to the vendors to understand which of the parameters are important?
So
like age and so forth.
Okay, sorry, I was muted, but so that is a really good question, and that's we haven't actually looked at high purity germanium failures, but I think that's a good fundamental question. What needs to happen is we need to identify those components that are prone to failures, and that's when I talk about data gaps. You know, a good example is if you have a turbo pump and you talk about monitoring that for temperature and those types of things, and you're able to say, hey, look, this actually gave me some good information. I can detect this early. But if, for instance, I'm looking at the frequency of the vibration of the pump, and I can monitor the resonant frequency and start to find that, well, I can actually tell this thing was going to fail way ahead of time. That's where I'm talking about. So we have identified things like that, like compressors, pumps that are prone to failures on radionuclide systems. So and yes, we do try to engage vendors when we can to get as much information about those components, because typically they will actually have a lot of information that they've done about when they're going to fail, that based on you know, their techniques that they use. Ours, I would say, are more on the analytical side, but I completely agree. That is something that you should be looking at. So.
Okay, so I think Ray, the question was posed to you, but I had a slide related to this in my presentation on data availability, where we talked a little bit about how we implemented some efforts related to high purity germanium detector by looking at things before. And the answer to the person posing the question is, you know, we, in conjunction with the vendors, have a lot of experience working with high purity germanium. And in order for a germanium detector to work correctly, it both has to have a good vacuum and it has to be at the correct low temperature, which is cryogenic temperatures, liquid nitrogen temperatures. So of course, the detector temperature is monitored. And as Ray pointed out, you know, we get a state of health every 10 minutes. So we know how the trend of this temperature is. So as we monitor this detector temperature, there are two models of how the detectors are cooled. Actually three, but in the case where they're mechanically cooled, there are two. One of the vendors has a cooler that has a constant power, and because the power is constant, it can't cool anymore. As you're losing vacuum or a defect is appearing, the temperature will rise. And by monitoring this before, that's an indication it's beginning to lose vacuum, and there's something you can intervene and do. In the other model, the power of the cooling system will increase. So you won't see a change in detector temperature, but if you monitor detector power, it's doing more work. So as this power keeps going and going, of course, it's a mechanical system. It doesn't have infinite power. At some point, it'll just give up, and then the effect of the defect will really begin to kick in, right? The detector will warm up because you don't have any more cooling power available. But if I can monitor the cooling power trend before, I know when to intervene, and then I do my vacuum restoration. The third model, which I talked about, is where we use liquid nitrogen. And in the case of liquid nitrogen, you basically have infinite cooling power. So for a liquid nitrogen detector, liquid nitrogen, you just consume more liquid nitrogen. So in that case, the thing that you want to see as an indicator of where is not the temperature or not the cooling power, you don't know what's going on, is the consumption of nitrogen. If I have nitrogen last 1 week on average, if I'm using it every 2 days to top off, my detector's losing vacuum. I won't see an effect, but it's using a lot of nitrogen. And those are the three types of cases where the advanced intervention can be done well before actual failure occurs. So yes, we as the experts are aware of these. We do work with the vendors because that's where the expert training comes in. We have special training from the vendors, which the station operators don't do, but we as people who do maintenance learn about these things and then try to implement them into the systems that we deploy. I hope that answered your question. That was a great question, but yeah, that's the heart of all of this. And really what needs to do is, we did it in sort of a crude way, but Ray's stuff will take all of what I talked and automate it, because that's what intelligent systems do, right? You can look for trends in temperature, but you got to train it on something. It doesn't know that the temperature is not supposed to go up. And when you train it to look for the trend, you'll find the fault. But we have been already implementing it in a non-artificial intelligence way, and with great success to manually do it and then intervene. Thanks. Okay, without that, we have a lot of time in this session, so it's a great way to talk about some of the questions that are really good and can't be answered, without going into some depth, because there's a lot of depth to the question itself. And I think it's the heart of the matter, which covered both Ray's talk and my talk. There's a lot of overlap in these two, because we're talking about, you don't just do predictive maintenance for the sake of it. Your end target in the end is improving data availability, right? That's the key thing in the mission of the PTS we want to do. So without much ado, I'll introduce our next speaker. It's Gernot Hartmann from the BGR in the Federal Republic of Germany. And Gernot will be talking to us today about operating a temporary seismic array during the modernization of an IMS station. Gernot, the floor is yours. Please go ahead.
This talk describes the installation and operation of a temporary seismic array while the primary seismic IMS station PS19 was modernized. At first, I will show the milestones of the 30 years history and why a general modernization was necessary. I will explain the technical details of our design of temporary stations and the seismic noise conditions. Then I present some results of data analysis which are of special interest if we want to evaluate the usefulness of such reduced array configurations. PS19 was established under the name Suarez in 1991. The nomination to serve as a primary seismic station PS19 for the verification of the CTBTO made an upgrade necessary in order to fulfill the requirements for an IMS station. This upgrade was completed in 2002. Technically, the station is an array with 25 elements within an aperture of 4 kilometers. The geological situation on outcropping granite, as well as a location in the less populated Bavarian forest, guarantees excellent background noise conditions. All array elements are connected by underground cables for power supply and data transmission with a central facility, where data are automatically collected and transmitted to the IDC. The station is operated remotely by the German NDC. In general, preventative maintenance is carried out twice a year. Nevertheless, after 25 years of reliable operation, PS19 needed to be modernized. Over the years, the power supply became interference-prone, mainly due to frequent lightning strikes. So, a comprehensive modernization was unavoidable and took place in 2017-2018. In total, 200 kilometers underground cable for power supply and data transmission were replaced. A new state-of-the-art system for overvoltage protection was installed. The whole infrastructure in the central facility was refurbished. However, this project made it necessary to shut down the complete data acquisition for 18 months. Since PS19 is the only primary seismic station in Central Europe, the shutdown would have had an impact on the detection capability of the IMS seismic network. That's why we decided to establish a temporary seismic array for the time of construction works. The installation should be carried out in self-sufficient mobile containers, easy to transport, but robust enough to withstand harsh weather conditions. Technically, the data acquisition system with digitizer and network router was installed in a mobile container. Power supply was provided by 2 fuel cells with 110 watts to charge 4 batteries with 100 ampere hours each. The charging cycle was monitored by the charge controller. The system consumed approximately 1 liter of methanol every 3 days. The fuel cell cluster controller automatically monitored the operational status of the fuel cells and the filling level of the methanol tanks and switched over to the other fuel cell or to the next tank if necessary. Remote control via radio modem ensured the immediate alerting in case of any irregularity. The seismometer remained in the original position in the fault. This slide shows the technical infrastructure of the temporary station illustrated with some photos. The seismometer in the fault is connected with a digitizer in the electronic cabinet in the mobile container by a cable. Furthermore, the arrangement of fuel cells, methanol tanks, and battery packs is shown on the right side in the mobile container. Only the antennas for radio transmission and GPS reception are mounted outside. In order to evaluate the recording conditions, we analyzed the ambient seismic noise. For that purpose, the probabilistic power spectral density, PPSD, is a convenient method. These are the PPSD plots for all 10 temporary array elements 4 months before and 7 months after the start of provisional operation. 9 stations were equipped with short-period seismometers. At station GEC2, a broadband seismometer was installed. That's why the PPSD plot on the right side is extended to longer periods up to 1000 seconds. Overall, we see no significant variations in the ambient noise conditions for periods above 0.3 seconds. Below that, the noise level increased after the change to the mobile systems. This means that the construction works at the array site as well as the operation of the fuel cells generate slightly more high-frequency noise. However, it isn't a predominant increase that would have dramatically disturbed the measurements of wanted seismic signals. The detection capability of an array depends on the number and spacing of the array elements. These properties can be derived from the array response in the wave number space. A preferable array response is characterized by a narrow, unidirectional main lobe with a wide rejection area without any side lobes. The Suarez array with 25 elements fulfills these requirements quite well. The 10 elements for the temporary array were selected from the 25 sites with regard to these criteria, but also logistical reasons had to be taken into account. The optimum array response was found for this configuration, shown here at the bottom left. The main lobe is only slightly elliptical deformed, and side lobes that decrease the array performance with respect to estimation of azimuth and velocity of seismic waves are only present at larger wave numbers and may only become relevant for signals with higher frequencies. On the right side, an example of the fourth North Korean nuclear explosion on January 6, 2016 is shown, where the Ceres beam is estimated with all 25 as well as with the selected 10 elements. Both beams are plotted one up in the other. The differences are marginal, as significant degrees of the beam amplitude can't be observed. We estimated the azimuthal residuals between the determined azimuth and the theoretical value for all events documented in the Reviewed Event Bulletin, abbreviated REB. On the left side, all events until April 2017 are shown when all 25 elements were used. On the right side, all events from May 2017 to October 2018 are included where the temporary array with 10 elements was in operation. Besides the different number of contributing events due to the different long time periods, a significant degradation of accuracy of azimuth determination can't be observed. Only beyond a distance of 100 degrees in the seismic shadow zone, the discrepancies in azimuth determination are larger, but visible for both array configurations. To see, for example, in South America or in Papua New Guinea. Let's have a closer look into the statistical details of the estimated azimuthal residuals. Here is the compilation of some statistics of the Ceres signal analysis. On the right side, we compare the accuracy of azimuth determination. The histogram shows the distribution of azimuthal residuals for events estimated with a 10-element array in light blue and for events estimated with a 25-element array in dark blue. The variability for the 10-element array is slightly higher. The left side diagram shows the overall percentage of REB events with Ceres phases on a monthly base between 2003 and 2020. The 18 months period with a 10-element array in operation is again shown in light blue. During this time, the mean percentage of events in the REB with Ceres phases decreased from about 20 to 15%. This is marked with the red lines. However, please note that most of the missed Ceres phases would belong to events with magnitudes below 5. In this magnitude range, the percentage dropped by 1/3. Since there are 75 times more events in the REB than with magnitude above 5, this number dominates the overall statistics. Taking only the events above magnitude 5 into account, the percentage of events with Ceres dropped only from 86 to 82%, which is still a remarkable number for only 10 elements. In conclusion, what was the intention? When a primary seismic station like PS19 had to be shut down for several months, for example for renovation, a temporary station should be installed instead in order to ensure the sustainment of detection capability of the IMS. Can such a project economically implemented? Yes, it can. The technical arrangement can be reduced to an essential extent, but should be robust enough to withstand the environmental conditions during the planned time span. For PS19, the equipment was self-sufficient and and automatic supervision of the operating status ensured the high data availability according to IMS standards. In case the concerned station is an array, as PS19 is, one should think about the necessary size of the subarray in order to preserve an acceptable array response. Then it is guaranteed that the station performance will not significantly decrease. The example of PS19 showed the continuous provision of seismic data from the only primary seismic IMS station in Central Europe was worth the effort to set up and operate a temporary array during the time of modernization.
Thank you very much, Mr. Hartmann. Very interesting talk about the operation, design, and performance and comparison of your temporary array. And thank you for the good work which enabled us to get data while the main station was being recapitalized. So with that, let's see if there are any questions. Let's see. Yes. First, we'll just wait if there are questions related to Mr. Hartmann's presentation. So while we're waiting, let me ask you one question. I guess you didn't give us an idea, but seismic arrays, especially large ones with 25 elements, 20 elements, have very expensive. I mean, you have individual sites, sensors, you have a borehole, you have power, some kind of container nearby, or maybe even a small building that's powering it, power system, and then all electronics, and then the communication system. We understand that a large station like that, the fixed structure is in the millions of dollars. But what was the cost of your temporary structure, and how? Because that's a driving factor. It has to be, it's a disposable thing, right? And it has to be worth your while to afford it, to do it. So give us some insights on how y'all did that cost-benefit analysis and made it happen.
Yeah, of course. This temporary array was designed for a long period, 18 months, with harsh weather conditions in that area. We have a long winter time there. So it was not so cheap as it could be, but it was 200,000 euros approximately for all elements. But you see, it's very the mobile containers were very heavy, of course. It's not so easy to bring them out. And so the monitoring system for the power supply and the online monitoring system, all the 18 months, was also not so cheap, of course, with the fuel cells. But I think for this dimension, it is worth to spend this money, because you see the result. We could provide a good data availability for the array all the time. We detected all necessary events. We have the 6 North Korean nuclear explosion detected very well. So the success of this temporary was it worth to spend this money?
Very good, very good. Thank you. So with that, I'll now we'll go back. There's another question that came up, and I guess I'll point it to Ray because it's really for him. And it asks, related to predictive maintenance and techniques and lessons, have you been able to tap into or pull something out from other industries which are more established and complex, like power stations or the automobile, modern automobile? Your car has this idiot light, the yellow orange light that comes on, and they meant us, the state of health, and then it tells you, check engine light. Yeah. I mean, it's something, don't drive anymore. If it's something simple, it's orange. If it's red, it's like, yeah, engine's gonna overheat. It's not an orange light, it's a red light. Yeah. So, but it's clever these days. It really does a lot of things and then only tells you when it thinks things are really getting severe. But in that regard, I guess the question is asking Ray, what have you been able to tap in and learn from these other established industries in this regard?
So, Michael, so that's actually a really good question. So we have done that. So there's actually a lot of papers that have been published in this area. So there's, I'll answer this in two ways, I guess. So when you talk about the example of the automobile, that's a really good point. It used to be that years ago, they would tell you every 3,000 miles you need to go change the oil of your car. But now they've gotten smarter and they monitor the condition of the oil, whether it's the viscosity, and they'll say, okay, hey, you actually have longer, you can go 5,000 miles, but it gives you a better estimate of the condition of the oil. And that's kind of what we're trying to do. But there's also the Prognostics and Health Management Society that they actually have ongoing conferences, and that's attended by General Electric, by NVIDIA, by a bunch of these big corporations, Intel, and they're looking at the exact same thing for different reasons. Big corporations, big plants actually use this because they're trying to ensure that these they're running. And so I guess the short answer is yes, we've looked at that. That's actually where some of the ideas that we have tried to implement have come from. So yes, that's a really good question. And we're definitely trying to leverage as much as we can from that industry.
Okay, so thanks, Ray. That was a good answer. I think in a more naive way, because the questioner actually addressed Ray and then he asked me if there was something I could say related to that, because my talk was a more broad talk about basically maintenance techniques and things that we've done in the past. And I think it's a good question because, in terms of maintenance strategy, coming back to the question about the example in the auto industry, in the old days, you changed your oil every 3,000 miles in the United States, or the equivalent kilometers. It was a fixed interval maintenance, or 6 months or something like that. Well, the current cars, you don't do that. There's an engine computer and it knows the number of times you stopped and started. It knows if you did short trips. It knows if you did long trips. It knows if the oil went to the right, high temperature. It monitors other conditions. Your engine is, getting a little bit too hot, or things may not be nice. And then intelligently, it actually calculates based on the vendor having done a lot of work that your oil needs to be changed now. And then at an appropriate time, it'll say in the next so many days or whatever, change your oil. So it's kind of predictive because it's really telling you to do something when it needs to be done and not do it because so many months or so many kilometers or just because, oh, I need to do, maintenance. That's very pertinent to the IMS because in the old days, that's kind of how we did things. We either did run to failure, probably the worst way to do maintenance because it's failed, so you don't have data. And the second one, when it's like, too late, yeah, a little bit, or you're doing too much maintenance because I'm going every year and just changing a lot of parts, and it's costing hundreds of thousands when it doesn't even need to be changed. So I think we're moving towards that. Intelligently or unintelligently, we're beginning to drive our vendors and ourselves in not doing things just unnecessarily, but because there's a cause or a known reason, and there's some kind of underlying model as to why that can happen. My talk was loosely based on all the practices, best practices and approaches, which would lead us to that. Ray's talk was about a more scientific, methodological, artificial intelligence-based software methodology, which would actually drive it using significant amount of sensors and trends into what you want to do. So it's sort of where we move into the future. But the question's a good question. It's really, that's, I think, in terms of sustainment of the IMS, we can't wait for things to fail, and we can't simply do things on a periodic basis because it's too expensive to do it. And we have to become more intelligent. And really, the heart of it is beginning to understand how much we can trust these automated systems, how quickly and well we can do it, and how effectively we can do it without sort of stumbling over our bootlaces and falling flat on our faces. You know, it's a new technology. It has to be incorporated. And that's exactly what Ray is trying to do, work with both the PTS and the vendors and slowly incorporate and get it in. And there are lessons learned from the other industries. And I'm sure, you know, some of our vendors now have backgrounds coming from very large industries. I know some of the noble gas vendors are also developers of large systems for the military and other things. General Dynamics, which has a RASA, is a big military contractor. So they have the knowledge and skills within their organization for, you know, obviously they build, you know, defense aircraft. You know, the F-16 is a General Dynamics thing, or, you know, things like that. Yeah. So obviously you can't just, you know, run the aircraft and then, it's the part to be changed or whatever. The knowledge is there, and how to take that appropriate knowledge and use it where it's applicable for the IMS. That's the key thing. Okay. And I'm not saying it's done. It's a challenge, and it's certainly an open thing. That's why we're having a scientific conference here. We'd like to invite people to come up and provide ideas, work with Ray and the PTS to make it better. It's, you know, Ray can't do it alone, and the PTS can't do it alone. It's you, the scientific community, which will drive it. So once again, please ask your questions. Please communicate with Ray. Please communicate with General Dynamics or the other vendors, with the IMS IDC on what your thoughts are, what you'd like to see happen, some timeframes and so forth. And also, when there's more interest from the community, it'll drive our management into understanding that, you know, people want this because we work for you. So, you know, if you want something, then we need to respond and we need to make sure that you have what you want. So keep that in mind. I think it's a great question. And with that, I don't think there are any more questions here. So we'll end the session. Again, reminding people, it's a conversation that this session has opened up. It's a scientific conference. Feel free to pose your questions on the site, or you can pose them directly to the speakers. Their emails available if you go into the program, and you can ask a question, and then a conversation will begin between all of you. Thank you very much for your time. Thank you. It was a very successful session, and please keep up the conversation. Please keep up the questions. Thanks. Bye-bye.